of this should be a review for you. How things grow exponentially. We have exponential growth, we have exponential decay. A good way to look at exponential growth is to take a piece of paper, and if you're constantly folding it in a factor of 2, you're folding it in half. So one fold is giving me 2 pieces. 2 folds is giving me 4 sections. 3 folds is giving me, how many do you think? Everything's doubling. 8. I should get 8 sections. See the 8 sections? And 4 folds should give me how many? 16. So, if 1 did 2, and 2, 4, and 3, 8, and 4, 16, everything was in a power of base 2. This is exponential growth. Versus linear growth, which is something that the rate doesn't change. It'll go up 2 every time. This went up 2, then doubled, went up 4 that time, then went up again to 8 that time. So this is not a straight line. This is going to be a curved line. At first it starts to grow slower, and then notice if I do 5 turns, 5 folds, I go to 32. Notice how fast it's getting. Oh, that's a cute look for you. 32. Notice how fast this is growing. It's growing exponentially. It's not a straight line. And over time, it's going to get higher and higher. Can you think of anything that grows exponentially or decays exponentially? Cells. Cells grow exponentially. How about, did you ever, open a bag of bread and it's got a little bit of green mold in it, and you say, oh, I'm not eating it. You put it back, but you didn't throw it out. And a couple days later, you forget. You open the bag again, and it's got a whole lot of green mold in there. That grows exponentially. Bacteria grows. We had nothing yesterday. Sorry. Right on that windowsill. I'm sorry. Sorry. Okay, so we're talking about exponential growth. Now, when we look at your exponential growth, this is the base. This is the exponent, the power that it's raised to. Okay, so your bases, well, they'll have the same look overall. Your base just makes it a little sharper. So if I was in a base 3, I would be doing 1, 3, 2, 8, 2, 9, 1, 3, 2, 9, 3, 27. Look at, I'm going to grow a little bit faster because your base is bigger. So the larger the base, the sharper the curve. It's all going to start looking at the same type of curve, but the sharpness of the steepness of it, and it's all going to depend on the base of it. So the next one might go a little bit steeper, then might be a little bit steeper up here. So you can see them starting to grow. Okay, let's get to stay. Alright, so today we're going to just look at exponential curves. Now you did this in Algebra 1, we did this in Algebra 2, and geometry now, but we revisit it again. And I spent a little bit more time up front with the exponents because logs are exponents, and they behave the same way as your exponents do. So if you kind of get back into your exponent swings, logs go a lot easier. So let's take a look at graphing these and see what kind of commonalities that they have here. So we did your one with a base of 2 already. So we said this is your exponent up here. What is anything to the 0 power? 1. So 2 to the, anything to the 0 is 1. 2 to the 1, 2, 2 squared, 4, 2 cubed, 8. We looked at this growth. Now, what does a negative exponent do? Make this be negative 1. Ah, gives me a fraction. Who said fraction? Good. Negative exponents. And this is one, when you forget what it does, always try this one. Put it in your calculator. You get 0.5. 0.5 in terms of 2 reminds you of what? 1/2. So therefore, what did this do? It took this and inverted this. That's all a negative exponent does. If I did 2 to the negative 2, it would still take this, it's negative 1 times 2. It would still take this, invert it, and then square it. And 1/4. So a negative 1 is just going to take the reciprocal. It's just going to invert it. And that's a good way to, if you forget what the negative does, just put a simple 1 in here. Because even though you see the decimal, it will remind you of the 1/2 that you flipped it over. Any negative exponent you have, separate it. Negative 1 times 4. Just separate this and then take it to the 4th power. The negative 1 takes it and inverts it. So with the negative 1, we get 1/2. You don't get any negative numbers out of here. It's basically taking this and just taking all of these and inverting them. And now we graph. Now, when you graph this, we're going to see a lot of common things with this. This is a common point right here. Let's put the 5 right under it. Let's do, I'm going to put another y down here, rather than just move it down because I'll lose all my work. This is going to be 5 to the x. So 5 to the x is going to behave the same way. 5 to the 0, 1. See this guy right here? Same exact answer. 5 to the 1st power, 5. 5 to the 2nd power, 25. 5 to the 3rd power, 125. And 5 to the 4th power, 625. Okay. The negatives work the same way. It's just taking the reciprocal. So, no negatives. 1/5. 1/25. 1/125. And 1/625. Okay, so now if we graph that on the same graph, notice how the left side got a little bit smaller than the other one, right? It got a little bit smaller. So over here, it's a little bit smaller down here. It still hits that point. From that point, the numbers grow a little bit faster. So it's a little bit sharper. A little bit sharper. But they keep the same curve, the same characteristics. And if we did a higher base, same thing. Be a little lower here, a little sharper here. Okay. Is this an increasing or a decreasing function? Increasing, right? Y is increasing. This is an increasing function. Y is increasing. Look at your Y values. It's increasing as we go from left to right. So your Y values increase as we go from left to right. A common point right here of intersection for your y-axis is the 0, 1. Because anything to the 0 power is 1. Will I ever get anything raised to a power that will give me 0? Like, can I raise this to anything to give me a 0? I'll never get the 0 out of there. So this x-axis is, what do we call this guy? Well, when y equals 0, because we can never get to the 0, so if it never touches it, what is it called? Asymptote. This is an asymptote. Good. Y equals 0 is an asymptote. It will never touch the 0. There's nothing you can raise 2 to the power of to result in 0. If we shift this down, yes, if we do, if we move this around, shift it down 1, yes, but right now, just with the parent, a core graph, there's nothing we can do for that. So your to the fifth power behaves the exact same way. What's the domain of this? All real numbers. And because we have an asymptote, what's the range? 0 to infinity. So if I say graph 10 to the x power, what would you tell me the range will be? 0 to infinity. What will you tell me the domain is? All real numbers. What will the y-intercept be? 0 when y is 0, when x is 0, what is y? 1. Okay. It will go like this. It'll be really, really, really small here and a little bit sharper like this. That's your base 10. Okay. So we see the same pattern for all your exponentials increasing ones. Okay. And this is a continuous function. Okay? All right. Basic type, little bit of a review for what you're used to doing for your graphs. Let's just recap this. So any graph, core graph, parent graph, whatever you want to call this, is going to behave the same exact way. And this is when this A has to be greater than 0. It has to be greater than 1 actually. Otherwise it's going to reverse what we're doing here. So I think I put that on the other page. It's greater than 0. If you look where at the very, I can't move it because I'll lose this. But A is greater than 0 and it's not equal to 1. Because 1 isn't going to help us out any. All right, so again, we have certain attributes. This guy, we'll look at this in a second with this negative. Now you want to pay attention to where the negatives go. The negative is next to the x. So again, you move your finger from right to left. It's from positive x to a negative x. So all this is doing is giving a reflection in your y-axis and making it a decreasing function. If the x negates, it goes from positives to negatives. It goes across the y-axis. This is a reflection in your y-axis. Your xy goes to your negative xy. These are your transformations, right? If it's next to the y, okay, then the y goes from positives to negatives. You have a reflection in the x-axis. We're going to do the same set of transformations that we did on your parabolas, your absolute values, your cubing functions. We're going to do the same rules for these guys. They work the exact same. They're functions. So we said domain for either one of these is all real numbers. The range for either one of these are the exact same. Can't use 0. The y-intercept, still the same. If it reflects over the y-axis, that point 0, 1 is on your y-axis. We said this guy was increasing. And what's that one? Decreasing. Good, God bless you. Your asymptote. What's your natural asymptote for this? The x-axis or the y equals 0? Same thing here. We didn't change this.
They don't want a point for the increasing, decreasing?
No, they just want to know if it's an increasing or decreasing function. It should say function at the end. It's an increasing function. And they're both continuous. They're both functions. They're both continuous. So these are your basic core graphs for exponential curves. It's your y equals 0, Jack, where it crosses the x-axis. Where the x-axis is at y equals 0. This little beauty, x-axis, y equals 0. It's going to be the same for both of them. It's like a natural asymptote, because there's no value that you can put in for x that will give you a y of 0. okay? Now, your transformations work right off of these. And when we do your transformations, we're going to keep keep track of where's your asymptotes, where's your point that we intersect, because that's a good point to use to see where it's moving to. So your transformations behave the very same as your other ones. We're going to start with your parent graph. So what would be your parent graph? Two to the x. So we're going to start with this guy first. We're going to graph this. We're going to do this without your calculator. You know it looks like this. Pass this through the 0, 1. This is y equals 0. This is 0, 1. Now, it works the same as your parabolas. Remember when your parabolas did this? And then we put it inside? Remember when it was next to the x? It made it move horizontally the opposite way. So, this is next to the x. It's going to move horizontally the opposite way. If it's next to the x, it affects the x. So it's going to move 5 places to the left. This is a good point to look at. 5 places to the left. And it's just going to have the same pattern. Just like this. 5 places to the left. That's why that's the only point that we have in common for all of our exponential curves, so we can really kind of keep track of that point. Now, the domain, did I affect the domain even though I changed the x value? No, because the domain was all real numbers. It was a horizontal movement, so I should not affect the range. The range stays the same. Because I didn't affect the range, I didn't change the asymptote. The asymptote is still the same. But the one thing that's going to change is your y-intercept. Your y-intercept is no longer at 0, 1. It can't be. Isn't that the point we moved over? Right? Now, remember how we found our y-intercept? We set x equal to 0. We're going to do the same thing here. So y is equal to 2 to the 5th. So it's going to intercept at the 0, 32. That's the one thing we changed because we moved it off of that y-axis. We moved it to the left. And we can kind of see that. It's got a ways to go before it intercepts your y-axis, right? Can you also confirm this on your calculator? Absolutely. The transformations, remember, try to do your transformations without your calculator. What happens when the transformation is outside of that x? Is everybody okay with this?
No, what you get 32?
We substituted in x of 0 because I want to see where does it intercept my y-axis. So when x is 0, then this becomes 5, 2 to the 5th. 2 to the 5th is 32. Put in 2 raised to the 5.
Oh, so you're 5.
No, yeah. 2 raised to the 5. You reversed it, yeah. We're still a base of 2. Good? Okay. By the time we do a couple, you'll say, oh yeah, I remember doing these. Okay, now it's outside of the x. When it's outside of the x, the transformation, what does it affect? The y. This is a vertical shift which way? Up. Because it's positive. So let's start with your core graph. Let's start with y equals 2 to the x. Basic core graph. We're just sketching. Remember, we sketch. This is a good point to keep track of. And this is a good thing to keep track of. The asymptote. If I do a vertical shift, is it going to affect the domain or the range? the range. So a good way to start is this. Start with your range from 0 to infinity. Start with your asymptote because these are going to be affected. Which way is this graph going to move? God bless you. Up 5. So take this point and go up 5. What should that point be? 0, 6. Good. And what should your y0 be? Y equals 0.
5, 6.
If I add 5,
Oh, y equals 5.
y equals 5. See this? Start like this. Aren't you moving everything up 5? The asymptote's moving up 5. The point is moving up 5. Now isn't this easier to graph now? So now your sketch has to pass through that point and go like this. So from here, everything that affected this affected the y value. So I add 5 to my range. So my new range becomes 5 to infinity. Did my domain change? No. My asymptote now also had to move up 5. There's my new asymptote. If it affects the domain, put everything you know about the domain there. And usually it's the 0.01 that you want to keep track of if it's the domain, since then nothing else in your domain will change for this guy. For your range, keep track of the two things that affect your range, your asymptote and the range. If I drop 5, instead of adding 5, what would I do? Subtract 5. I would drop 5 over here. I would drop 5 over here. So if I was dropping 5, for instance, I would drop this point, 5. This would be at the 0, -4. I would drop this 5. This would be at the y equals -5. Do you see my graph? And my range changes, and my y-intercept changes. Good? Remember your transformations? We use your transformations all the way through the year. And it makes sense if you use your transformations to help you graph these. Okay, let's try this guy. This is our last one. What's the negative here? What's your parent graph? Start with 2 to the x. So let's start with that graph. Okay. Again, here's my point. We know very little about this. Now, this negative, if the negative was by the x, if the negative was here, then my x goes negative to positive. My reflection would be where? Well, it would go to the left, so it would go over the y-axis. But it's not by my x, it's by my y. When the negative is in front of it, it's closer to the y. You're going to put the x in, and then it's going to affect the y, not the x value. In other words, if I put a 1 in there, 2 to the 1 doesn't affect the x, but then the negative affects the y, the result of it. So I'm changing the y's positive to negative. So where's my reflection going to be? Over the x-axis. Good. So this point is coming down here. This point here. Here, here, this point here, going like this. There's my reflection, but without the little bump in it. There's my reflection over the x-axis. Did my domain change? No. Did my range change?
Yeah.
What's my new range? Negative infinity to 0. Good. Because now I'm coming from up here, up. I got stuck at the 0. Can't use 0. Did my asymptote change? Still y equals 0. So we apply your transformations the same way we did to a cubing function, a squaring function, a square root, an absolute value. We use the same concepts. My advice, guys, you really have two things. The y-intercept and the asymptote. Make sure you keep track of those two things during your transformations. And use the fact if it's going to affect the domain or affect the range. If it affects the range, it affects your asymptote as well. Okay?